Hello, this video corresponds to Chapter 5 and is intended to introduce probability and hypothesis testing and the relationships of both of those things to inferential statistics. So first let's talk a little bit about probability. First we have personal probability, and it's also known as subjective probability, and it's your own personal estimate of how likely you think it is that a particular event will happen. Like, how likely is it that tomorrow it will be above 80 degrees? Well, if you are in the Midwest right now and it's July, then it's pretty high likelihood. But we don't have any basis of data to help us really necessarily make that judgment. It's just that we kind of go with our gut instinct, unless we're a meteorologist or something. However, that's very different from what we mean when we talk about probability and we talk about inferential statistics. What we're talking about with probability is really the expected relative frequency probability, which is what is the likelihood of a particular event occurring if we were to repeat multiple trials. So repeat a particular event many times. So, for example, if we were to sample from a bowl of marbles, and there are black marbles and there are red marbles, and there's only 10 black marbles and there's 100 red marbles. In the beginning, we would expect that it would be more likely that we would get red marbles, but we could still get some black marbles if we were to only draw one. But the more trials we have, the probability of getting a black marble is going to approach the ratio or the likelihood that we have, we've drawn one of those 10 out of the total number. Additionally, we have to consider the role of independence and probability. And if you're at all familiar with talking about these kinds of things in terms of independence and probability, you might be familiar with the gambler's fallacy. But first, before I explain the gambler's fallacy, let me give you a couple of scenarios. So, do you agree? The very first one. That woman has been playing that slot machine without success for 2 hours, and she just quit. Let's play that one. It's going to pay off soon. Do you think that that's true or not? Okay. And the second one. My next door neighbor has 3 boys and she's pregnant again. This one is bound to be a girl. So, do you agree with that statement? If you said that you agreed with either of the statements, then you're falling prey to the gambler's fallacy. The gambler's fallacy is the mistaken notion that the probability of a particular event changes with the long string of the same event. So in the first example, the fact that that woman had been playing at the slot machine for quite a while and she hadn't at all won, that the likelihood that she's going to win in the future is going to be greater. Same thing about, you've got 3 baby boys, this one's bound to be a girl. Well, again, it doesn't have anything to do with the previous events. Probability is not certainty. And the thing we have to remember here is that with the gambler's fallacy, the events are independent. Every pull of the slot machine's arm is going to be independent from the previous pull. So the likelihood of a win on any given pull is the same. Same thing with gender of babies, that the likelihood that you'll have a boy or a girl on any given pregnancy is the same across pregnancies. It doesn't matter if you have this pattern. Of course, biologically speaking, there are some factors that play a role there. But if we were just going to talk about independence, just because you had a girl before does not mean you're bound to have a boy. Okay. Probability is also not certainty unless the probability or ratio is 1 or 0. 1 means it's definitely going to happen, and 0 means it's never going to happen. Those are your only 2 options. So there's no certainty with probability. It's just that the likelihood of a particular event changes. The closer it gets to 0, the less likely it is, and the closer it gets to 1, the more likely it is. Probabilities are long-run patterns, and they are not guarantees of what will happen. It just gives us a sense of what's the likelihood that a particular event might happen in the long run. So this brings us to the next thing, is confidence. In hypothesis testing, probability is a rating of our confidence that this event will occur. Okay, so if you get a statistically significant result, you're pretty confident that the difference you found is unlikely to be due to chance. So really what we're trying to do is use probabilities to make decisions about hypotheses. So that's where inferential statistics come in. What we do is we use the rules of probability to test hypotheses. And using probability, we're asking the question of how likely is it that we drew these two groups out of the same population. That's a test of the null hypothesis. And we use what we know about probabilities to make decisions about whether or not we think they're different or the same. And we'll get to that in a little bit. But first we need to talk a little bit about how do we arrive at calculating probability. So you determine the total number of trials. Let's say that we go back to that marble example and we have we decide to draw 10 marbles out with replacement. So we determine that we've got 10 total trials. And then we determine that a successful trial is when we draw a black marble. So we figure out how many of these trials, these 10 trials, are successful outcomes. So we draw repeatedly a marble out of that pot, and we write down the number of times that out of 10 that we draw a black marble. Then we take that number of successful outcomes and divide it by the number of total trials. So if we drew a black marble twice and we had 10 trials, then we would say that the probability of drawing a black marble is 20% or 0.20. We might do that 100 times. And in this case, perhaps we drew 10 black marbles and out of 100 trials. So in that case, we would say, oh, well, the probability is 0.10 or 10%, which is actually what the case is in terms of the population, or more or less. Okay. So how does this fit in with hypothesis testing? Well, we need to learn first how to develop hypotheses and how to think about what we're testing. We're actually testing, when we do hypothesis testing, the null hypothesis. It's kind of dull and boring, so you can think of dull and null as going together. And it essentially says that there's no difference between the groups. It's not the thing we expect to find. The relationship that we expect to find, or that we hope to find, is the research hypothesis. So let's say that we have a group of high school students who are being tutored in math, and we want to know whether older adults are more effective than college students at perhaps tutoring students in math, these high school students. So who are they going to be more receptive to? So perhaps we have some sort of traditional after-school program that does have older adult tutors, not younger tutors that they maybe can relate to better. So we might consider that to be our control group, because that's what we already have in place. And the people who are tutored by college students are in our experimental group. And that's the treatment that we're really interested in. Sometimes our control group is kind of the standard treatment, and sometimes our control group is people don't get tutoring at all. So it could be the absence of treatment, or it could be our treatment compared to the standard treatment. So if we're thinking about two different groups, then we can talk about one being the control group and one being the experimental group. So let's say we want to develop these hypotheses. Well, we first need to develop both null and research hypotheses. The null hypothesis, again, remember, is the boring one. And so we might state that our null hypothesis is that high school students who are tutored by college students and older adults have the same exam grades. Okay, so there's no difference here. And if we stated this symbolically, we would say mu sub 1, mu for population 1, is the same as mu sub 2, equal to mu sub 2. So here our two populations are high school students who are tutored by college students, and the second population is high school students who are tutored by older adults. In the research hypothesis, this is where we find the interesting stuff. And in this case, we're saying high school students who are tutored by college students have different exam grades than those tutored by older adults. And we don't really know what the direction of the relationship is. Notice that we're saying they're either the same for the null hypothesis or they're different for the research hypothesis. Because we're not saying that we think college students would be better because we don't know for sure. And we're not saying that we think they're going to be, the older adults are going to be better either, just that they're different. So it leaves us open to that possibility of difference. If we wanted to state these hypotheses symbolically, then we would say H sub 1, where you see mu sub 1 is not equal to mu sub 2. And that's how we state that they're different in symbols. So let's take a minute here to work through a couple of examples. What I'd like you to do is to write down the two different populations we're comparing, and then write your null hypothesis and your research hypothesis. So go ahead and pause the video and take a moment to note the two different populations and your null and research hypotheses. Okay, so the first population is Canadian children in general. So we're comparing them to the second population, which is Canadian children whose parents are librarians. For the null hypothesis, we would say Canadian children whose parents are librarians have the same reading ability as Canadian children in general. And for the alternative hypothesis, we'd say Canadian children whose parents are librarians have different reading abilities than Canadian children in general. Again, notice that we say that they're the same for the null hypothesis and that they're different for the research hypothesis. Here's another example. So go ahead and pause, note the populations and your two hypotheses. So our two hypotheses here, our two populations here, are people who have experienced earthquakes, and the second is the general population of people. And our null hypothesis is that people who have experienced earthquakes have the same self-confidence as the general population. And the research hypothesis is that people who have experienced earthquakes have different levels of self-confidence from the general population. Okay, so the last part about this is making a decision about the hypotheses. We're always testing, as I said, the null hypothesis, so the one that they're equivalent. And we can make two different decisions about our null hypothesis. We can either reject the null hypothesis, which means that we found evidence that supports our research hypothesis, or that we found a difference, or we can fail to reject the null hypothesis, which means that we have no evidence that the two groups are different. I know it's kind of a strange way of thinking about these things, but since we're always testing the fact that they're the same, and there are many, many ways that they can be different, then there's only one way that they can be the same, is that they essentially have the same means. So when we reject the null hypothesis, we're concluding that we found a difference, and when we fail to reject the null hypothesis, we are concluding that we did not find a difference. So in our case, if we tested a null hypothesis that the college students the high school students did better when the college students tutored them, that would be rejecting the null hypothesis. Okay? But if we found that their exam grades were the same, then we would say that we failed to reject the null hypothesis, and it didn't matter whether the tutors were college students or adults. So next time we will talk a little bit about statistical inferences and how they can be wrong. Because remember, we're talking about probabilities here. And the next video introduces type 1 error and type 2 error and relates it to hypothesis testing.